So we'll be talking about autonomy system today. We are providing the system to everybody. Okay. So the work started from SLAM several years ago, and we worked on Lidar SLAM. And this is what we got in 2015. This is where we started. We worked on something called LOAM, Lidar Odometry And Mapping. So that's a 3D LiDAR on top of my head. That's myself. Jumping over that electrical vehicle. And there's an IMU inside the 3D LiDAR. We were able to process the data, estimate the trajectory, and building a coherent point cloud map of the environment. This is the final point cloud from that SLAM algorithm. And this is manually labeled just to show the accuracy of the scan registration. So we were able to do this in 2015. And from there, we wanted to move on to autonomy. We only had SLAM, but what we did was connecting SLAM to a flight controller or a path follower, and we put it on a drone, and we were able to fly it autonomously. Right? So this is that drone flying. It's not a full autonomous system. It's just following manually defined waypoints, but it's flying autonomously. Okay, so in that sense, so that's me again. So in that sense, this is autonomous system just by connecting SLAM to a path following flight controller, and we got our first step into autonomy. Okay, and it really got us on the road to develop the autonomy system. Okay, so this is where we started. And it got us on the road to develop this autonomy system over the last few years. We started from SLAM, and our SLAM kept developing. And today we are calling it Super Odometry. Shibo will be talking about it this afternoon. So Shibo is the organizer. Please check it out. And we are going to focus more on the autonomy side of the system. So on top of SLAM, we build up multiple layers. So we first have this mid layer with 3 modules. They are all fundamental navigation modules. The mid layer is meant to be providing the fundamental navigation functions for terrain traversability analysis to analyze the terrain and segment the terrain into traversable and non-traversable. It's just for ground vehicles. Okay. Aerial vehicles don't need to analyze the terrain because aerial vehicles don't touch the terrain. Aerial vehicles only need to know the free space. But ground vehicles, because it's touching the ground, it needs to actively analyze where is traversable and where it's not traversable. That's what we call terrain traversability analysis to segment the terrain. Okay. Clear avoidance to plan passes, local passes in front of the vehicle, and to guide the vehicle through obstacles, nudging the passes in front of vehicle to make sure the vehicle does not hit anything. So that's basically what clear avoidance does. And path following control. Okay. Well, we had these 3 modules, and on top of it, we start to build. And on top of it, we started to build this top level, this high level modules. So modules at the high level, they are targeted at particular applications or missions. So here we're listing 2. We have exploration and route planning. The exploration is to send the robot into the environment, and it goes to everywhere. In the end, it builds a full map of the environment. That's what we call exploration. And route planning sends the robot to a goal point or multiple goal points. So if you look at these 2 planners, they are from 2 main classes of navigation problems. The exploration, we say, it's from the class of problem called coverage. We send the robot in, it goes to everywhere and builds a map. So it's covering the environment. And the route planning, it's sending the robot to a sequence of goal points or just a single goal point for something like a delivery to go somewhere to deliver something. Okay. So that's the overall structure of our SLAM system. And we have the system, it's open source, we're providing it to everybody. What we're doing here is to support everybody's work. And we want to use it to support advanced AI. If you work on the advanced AI, you're most likely working on the high level in the system, because AI is at the high level, and you don't necessarily have to spend time to build the base navigation system. That's what we are providing here. Where we don't expect everybody to be able to build the system from scratch and for all the parts. If you're focusing on the high-level part, the AI part, you can utilize the space navigation system from us because it's our specialty. Okay. And why are we doing this? So I would put something in called technology readiness level, TRL levels. So this is a chart with 9 levels, and we use it to evaluate how ready a technology is to be used in users' hand. The bottom part, the orange part, we call it fundamental research, proof of concept in the lab. The middle one, in light blue, this is getting interesting. The technology goes out of the lab and being evaluated in the field. The dark blue, we usually think of it as stepping into the industry and getting into the user's hand. Okay. So what we are looking at here are these 2 levels, the level 6 and the level 7. So this is the step that getting out of the door of universities and getting into the industry. So let's read these 2 levels. So level 6 says, technology demonstrated in relevant environment. So if you don't evaluate your technology in the exact operational environment, if you don't have that condition, or if you don't want to do it, you can evaluate your technology in a relevant environment that looks similar to the real operational environment. And by doing that, you're at level 6, okay? But if you do evaluate your technology in the operational environment, you're level 7, okay? You're 1 level up. So what's the difference here? The difference really is the testing environment. It could be the same technology and same prototype. These 2 levels, they don't distinguish the technology or the prototype. As long as you operate in the operational environment, you're level 7. So what we're doing here, back to our story, we are essentially providing this space navigation system with the fundamental navigation capabilities to assist everybody's work, to help you realize your technology in the real environment on the real platforms, and pushing your technologies up level by level through this chart, and eventually getting into the dark blue part, into users' hands. Okay. So next, I'm going to use 2 slides to show 2 high-level functionalities or capabilities. We're showing exploration here as the capability of the system as a whole. And in the next slide, I will use a simulation demo to show the route planning. So we don't have the time to go through all the details in the system modules. We have a few backup slides in the back. If you are interested, you can download the slide deck and you can look at it, or all the information is on our website. We will give out the web link in the end. So here, this is the exploration. It's one of the 2 main functions of the system as a whole. The vehicle goes into this environment and it explores. Our system works in simulation and it works on real platform. This is our own real platform. It's a wheelchair-based vehicle. We bought the wheelchair, we retrofit it, make it a drive-by-wire, and we build our own. So this shows the planning, the exploration planning. It's constantly replanning the blue paths to guide the vehicle through the environment and to explore. The on top of the robot is the 3D LiDAR from Velodyne. And there is IMU in the blue box. There is the i7 processing computer in the blue box. All the processing is happening on that computer in the blue box. And now this is after exploring the garage that got onto a patio connected to the garage. Here we're showing the local planner, local planar avoidance. Okay. And this is covering the other side of the patio, and this is to the end of the exploration route. Okay. Now we are seeing the whole exploration process starting from the top of the garage, going level by level to the bottom. Here is the bottom. And now it's circulating back to the top of the garage. And it's getting to the patio right now. Here is the patio. And it's returning back to the front. Here is the Compatibility map review with the vehicle trajectory. All the processing is happening on board the computer in the blue box. And by the end of the run, we have this Compatibility. And this is our navigation system. And our okay, for now, I want to switch to my other computer to show a simulation demo. So, this is demonstrating the other capability, which is to to go point. Okay. We call it route planning or go point navigation. So this is our navigation system running in simulation. We're looking at this left part. This is about the navigation and the planning. The right part, these three images are rendered by the engine. It's called AI Habitat Engine. And we're using a environment model from Metaphor 3D as open source model. So here, I can give a goal point to the system, and it's planning the path. The system can start in unknown environment, knowing nothing about the environmental layout. It figures out its way as it moves around. It keeps looking for the better path, and it builds out its own graph. Now, the blue path is the global path from the route planner. Red and green are from the visibility graph, which is our global route planner. Okay. So it's trying out a few ways. It's getting into dead ends, which it does not know. But once it figures out, it corrects itself by replanning and guiding itself to the goal point eventually. Okay. Okay, at this point, it has got to the goal point, and I can give another goal point here, and it will keep planning. If it does not know the environment, if it's going to a new environment, it replans and it figure out the way on the fly. But if it's going to somewhere that it has been to, it will figure out the way immediately. Because this part has the graph coverage now, and it does now need to fly and to figure out the environmental layout. Okay, so that's the navigation to the goal point by our global route planner. Now there's another feature in the system, which is to use a joystick to drive the vehicle. We call it smart joystick. Now I am going to push this button to this joystick to teleoperate it, and this is directly interfacing with the local planner, the local clear avoidance module in the system. You can give it a rough direction. Okay, you can give it a rough direction and push the joystick. It figures out the clear-free way to go. Okay, so this is the cooperation between your input through the joystick and the clear avoidance module. It's trying to follow your command, but it's also making sure it's not running into anything. Okay, so we found this to be useful feature for debugging and for some of the applications actually. And if you want to resume the navigation to the goal point, you can click here, resume navigation to go, but it will go into the original goal point, or you can give it a new goal point. Or you can use this virtual joystick, which is the same with this one. These two are the same. So you can teleoperate it here. If you don't have a physical joystick, you can use this virtual joystick to try out our system. Okay. Okay. Now I will switch back to my slides. Okay, this is the route planning. We saw the simulation demo. And here I will quickly talk about how to use our system. Okay, we support multiple open source Lidar SLAM approaches. They are open source. We support all these listed here and more. Our own Lidar module is called Super Odometry. It will get released in the next few months, and by the time that it gets released, it will support the system, of course. And do check it out and use it. We support multiple types of platforms. Okay, there are all kinds of platforms out there. We support by default the differential drive platforms, which is the top row here. That's what we support. The second row are the omnidirectional wheels. Omnidirectional platforms, including the electric robot. So these platforms, they can go sideways. Our system supports it, but it does not fully utilize the fact that it can go sideways. It still tries to drive it forward and turns the vehicle and drives to another direction. But they are supported. So omnidirectional platforms are supported. The third one is a little bit problematic. The car-like vehicles with steering wheels, that's the one on the bottom. So for these vehicles, we only partially support it because we only support one-way drive. The car-like vehicles, if you drive it into a tight space, every once in a while, it needs to back itself and to turn in another direction. So we call it three-point turns. Our system does not support three-point turns by default. Supporting it needs some modification to the code. It's possible, but by default, the open source version does not support three-point turns or the car-like platforms fully. Okay. So our whole system is open source. We're listing the web link on the top, cmu-exploration.com. A good number of users are trying it out. And we got all these pictures from our users. When they ask us questions, they send us a picture to tell us what they're doing every once in a while, and we collected this, all these pictures. And you can really see that all these users, they're trying many different things with our system. And if you look at this, one on the bottom, in the middle, now on the bottom, it looks like two military vehicles driving in a vineyard. I will very quickly show 3 use cases, just 3 topics. Everybody here using our system has a better idea of how to use it to facilitate your work. We're just giving 3 example topics. So first one is social navigation. You can insert human avatars into the system and to try developing your algorithm that drives around people walking around. Mixed initiative navigation with human interactions. You would develop a module that interacts with people through languages. The robot asks the person a question, how can I get to somewhere? And the module listens to the command or the directions from the person and interprets the language and uses our base navigation system to navigate and to avoid collision. Okay. And another popular topic, sim to real navigation, bridging the sim to real gap. You would upgrade the simulator in our system to a more realistic simulator, or replace the environment model in it by a model that matches your testing environment. And from there, you can develop your own algorithm or your models in the simulation using all the navigation functions in the system. And eventually, you can put it on your real robot and test it in your real environment and see how it works. Okay. So in the end, our system has been used in traversability challenge. A couple of years ago, we had the final, and our team was the one that made the most complete exploration in the final. Among all the teams, we made the most complete map, and which is the map here, made by 3 robots. The 3 trajectories here, the red, green, and blue, are from the three robots, and this really shows the strength of our system. It's a working and a reliable system. And now it's made available to you to use to facilitate your work. Okay. Some papers, if you are interested in the technical details in the system, you can look at these papers. But if you just need to use the system as a tool to facilitate your work, you don't necessarily have to read these papers. The system is made easy enough for you to use as a tool. And that's all. Okay. And please give it a try and see if you can use the system to help your work. Okay, thank you.